This is the first macronutrient section. So we've talked a little bit about energy in general and then energy specific to food and how to calculate calories. Now we get to go through and we're going to look first at fats and oils, this first macronutrient. We're going to see what the structure looks like. We're going to see the differences between fats and oils. We're going to look at saturated and unsaturated. We're going to look at how food is affected by the type of fats and oils that are in it. We're going to see how they can figure out how much unsaturation there is. We're going to talk about cholesterol. Oh, so many things you're going to learn about fats and oils. Let's look at the structure for those fats and oils and let's see what some of the differences and similarities are. Well, first we want to start with the similarities. Fats and oils are both what we call a triglyceride. That's just a triester of glycerol. Ester means that we have this functional group. It's got a hydrocarbon attached to a carbon, double bond oxygen, attached to another oxygen, attached to another hydrocarbon. Oh, it looks big and crazy. But what's going to happen is that whenever this fat or oil was first made, it starts with a glycerol. Glycerol is these 3 carbons right here, and they have 3 OHs. Those OHs react with a fatty acid to make a triglyceride. So we end up with this one really, really, really big compound. And if you remember from way back when, these R's mean that we have a long hydrocarbon chain. Now these hydrocarbon chains may be the same, but they can be different. If you notice, they've actually indicated them as R, R prime, and R double prime, meaning that most likely they are different. They might have different lengths of the chain. They might have double bonds or single bonds. Each one is slightly different. Now, because we have all these differences in the side chain, this is going to bring forth a really kind of unique thing about fats and oils. When you talk about corn oil or vegetable oil or canola oil or whatever type of oil you want to talk about, that oil is not just one compound. That oil is actually a mixture of all of these different complex compounds, complex structures that have come together. Even if you look within one fat or oil molecule, the side chains are even different. So what you'll find is that they'll be similar to one another, because here we go back to this idea of volatility to make sure that they're all kind of similar, but there's a very complex mixture of them. Now, depending on what side groups you have, that's going to determine whether you have a fat or an oil. And what we're going to base it on is, well, in your mind, what is the difference between a fat and an oil? Well, we talked about vegetable oil, olive oil, canola oil. Those are all things that you can pour. They're all liquids. And fats, generally, we think of fats as being solids, and that is the general rule of thumb. A fat is a solid and an oil is a liquid. But what makes it a solid versus a liquid? It turns out there's 2 main reasons that we're going to talk about. The first is the length of the chain. If you increase the length of the chain, meaning if you increase the number of carbons, you're going to increase the melting point. Okay, so does that make it more likely to be a fat or an oil? Let's add some stuff in here. So we said that the solids are generally fats. The liquids are generally oils. Now we have some exceptions in there that we'll talk about. So the melting point is going to be above or below room temperature, excuse me. If it's an oil, your melting point is below room temperature. That's why it went ahead and melted. And if it's a solid, if it's a fat, your melting point is above room temperature because it hasn't gotten to that melting point yet. So the length of the chains can make a difference. And again, that's just how many carbon are in this long chain. The more carbons, the higher the melting point, the more likely it is to be a solid. More likely to be solid. And solid, of course, is going to be a fat. The other thing we can look at is the degree of unsaturation. This is the number of double bonds that are in that particular side chain. And we're going to talk about this a lot more in the next couple of slides. Now on the bottom it says if you increase unsaturation. So that means if you increase the number of double bonds, it says it decreases the melting point. That means it's more likely to be a liquid. It's more likely to be oil instead of a fat, a liquid instead of a solid. Okay, we'll get into that a little bit more over the next couple of slides. This one's looking at that idea of saturated versus unsaturated fats and oils. Now, from your experience, do you think of one as being bad and one as being good? Is one healthy and one not? What experiences do you bring into this? Well, normally they will say that saturated fat is bad and unsaturated is healthier fats. What does that actually mean? Saturated means that you only have single bonds. It's saturated. It's full of hydrogens. There's no place to put any more hydrogens. So again, only single bonds. Now, on the top right, we're trying to show this idea of a saturated fat. And here we're just looking at one of those little side chains. Remember, an actual fat molecule will actually have 3 of these side chains. Now this has a long hydrocarbon tail, so let's circle it. Big old long hydrocarbon tail. Now, if you remember from earlier in the class, this is used to represent those different elements, the different atoms within the different elements. So the little black balls are carbon, the little white ones are hydrogen. So this is actually a chain of a whole bunch of different carbons with hydrogens attached. Notice each carbon has 2 hydrogens. Now at the very end, we have the carboxylic acid head. So we have a carbon, double bond oxygen, and then we have our OH. If it was an actual fat molecule, instead of having that H, we'd have a carbon, the 3-carbon triglyceride type ending. Now, the number of carbon will vary depending on the individual side chain that you're looking at. But when we talk about saturated, it just means that they're single bonds. So I could write that. So here we have C double bond O, there's an O here, and whether you put the H or the R, whatever. And then there's just a bunch of carbons. So however many carbons you want to put in. And on each of these carbons, remember they like to have 4 bonds. So they have 2 bonds with other carbons. And so you'll put 2 hydrogens on them. So I'm showing this as just one straight line. But whenever you actually put those carbons together, the actual atoms, they tend to like to zigzag back and forth. And so we can see that zigzag a little bit easier in the model above. Now we also have another model, so those are equivalent to one another. They just look a little bit different. But one of the challenges that you have is to be able to see that even if they look different, they're actually the same. Now here's another way that we could show this. This is a space filling model. So this has the carbons in the center, the hydrogens are on the outside, but it's showing how the atoms are actually going to be closer to one another. There's not as much empty space between them. Now also for this one, again, we're talking about that saturated fat. It's going to show an example of chocolate. It says chocolate's rich, creamy, melt on the tongue texture derives largely from the nature of its fats. Stearic acid makes up about 1/3 of the fatty acids and the triglycerides of chocolate. On the bottom, we have our unsaturated fatty acid that we want to talk about. Unsaturated means that it's not full of those hydrogen. We could add more hydrogen if we needed to. And the reason we're able to do that is that it has a double bond. So 1 or more double bonds. So if you have a polyunsaturated, it has more than 1 double bond. Now we generally consider unsaturated fatty acids to be healthier. So we have some examples of avocados and also almonds. And down on the bottom, we actually have the structure drawn out. We have the ball and stick model, and then we have the space filling model. Now notice on this one, it's not a straight line anymore. There's a kink in it. And that kink is because there's a double bond. But one thing that you're going to notice is that even if there's a kink, the carbon are both going to either be on top or below that kink. On this case, they're both below. The hydrogens are above. So we can get into this idea of what's called a cis or trans that we're going to see here in just a little bit. But the thing to recognize right now is that in an unsaturated fatty acid, there is a kink because of that double bond. And that's going to affect how well they can stack together. So how does that saturated or unsaturated affect how those different molecules are going to stack together? At the top, we're going to be looking at the saturated fatty acids. Remember, these only have single bonds. They're going to have more what we call intermolecular attraction, meaning between atoms of different chains or between atoms of different molecules, we have some temporary attractions that are going to be shown. Now, these temporary attractions, they're trying to show them in green right there. Notice they're just little bitty dashes. So these might be some hydrogen bonds or maybe some London forces, whatever the case might be. In general, your saturated fatty acids have higher melting point, meaning that they're more likely to be a solid at room temperature, and we call those fats. Unsaturated at the bottom has a double bond, and because it has a double bond, that's going to cause kinks to occur. Now, because we have a kink, that means that it's not going to stack as nicely. I mean, look at that. They don't stack very nicely together. They end up having lots of volume or room that's going to be lost. Now, because we're increasing the volume, we can actually see how it would affect density. There's going to be less intermolecular attractions because those chains aren't as close to one another. Now, overall, this is going to cause a lowering of the melting point, meaning that if we have those kinks, if they can't stack very well, these are going to be things that are more likely to be in oil. So most of our oils will have these unsaturated areas or these double bonds. Now, it's not enough to just say, yeah, it has double bonds or no, it doesn't. Sometimes we want to know how many double bonds it has because that can affect, well, how well those are going to stack together. To help with that, we use something called an iodine number. Now, iodine, if you remember, it's one of the elements of the periodic table, and if you also remember, it's a diatomic molecule, meaning that if it's in its free state, it likes to be I2, not I by itself. Oxygen is the same way. We can use iodine to measure the degree of unsaturation, or we can use it to measure how many double bonds there are. Now, the way that we do this is they take, in general, 100 grams of your triglyceride, so 100 grams of the fat or oil that you're testing, and then you're going to add some iodine. Now, iodine normally has a red-violet color. So if we look at the equation on the bottom, here's iodine, this I2 to iodine. Now, this is generally going to be a dark color. It's like a dark violet reddish color. And if we add it to something that has a double bond, those iodines are going to come attack that double bond. And they're actually going to form bonds, and it breaks that double bond. Now, when it does that, instead of having iodine be this dark purple color, it's going to make something that no longer has any color. So the more double bonds, the more iodine is going to be changed. So the more iodine that's changed, well, that's the more iodine that could have been added. The iodine number is higher. So here it says the oil's iodine number is greater than fats. So oils are more likely to be unsaturated than fats are because they have a lower melting point. They have more double bonds. You can add more iodine to those. Let's see an example. I like seeing the visual of this example. So to start with, we have two different oils. We have peanut oil on the left and we have sunflower oil on the right. So peanut oil, you'll hear about that being used for frying things, especially if you have a big deep fat fryer. Peanut oil is a really good oil, a really good mix of those different compounds to use at that particular temperature. On the right is sunflower oil, which you don't actually hear about as much anymore. Either way, they measured out a certain amount of both of them. In the lab, it usually says 100 grams. And then what they did is they added the same amount of iodine to each of those. Now, if you give it just a minute to react, let it sit for just a little bit, that iodine, remember, it reacts with the double bonds. So on the bottom, you can see which one reacted and which one didn't. I'll walk you through it, don't worry. So if we look at the bottom, you see that the one on the right is now colorless. We don't see the iodine anymore, meaning that the iodine molecule, that I2 molecule, was actually broken or separated, and it actually combined with that fat or that oil. That means that there had to be a lot of double bonds. So since the one on the right is colorless, that means that it had more double bonds, that it's more unsaturated than the one on the left. So we can use this technique to try to give us an indication of the number of double bonds or the degree of unsaturation. Here we have different examples of fats and oils. Fats are on the top, remember they're solids. The oils and liquids are on the bottom. So the first fat that's listed is, oh, wait a second, coconut oil? Oh, how's this going to work? We consider it to be an oil, but if you look at it at room temperature, it's actually solid, or they'll call it a semi-solid state, melts just above room temperature. Oh, so this causes a problem. Well, not a problem, but it just leads you to the idea that science can be more complex than we really like it to be sometimes. With the coconut oil, if you notice, most of it's red. So most of this is red, and that red means that it's saturated. It has a little bit of monounsaturated, that means that we have one double bond, and a tiny bit of polyunsaturated, meaning that some of those little side chains have more than one double bond. So your coconut oil, palm kernel oil is the same way, very much saturated with a little bit of unsaturated, but on both of those, they melt just above room temperature. Now they're unusual in that they have a large amount of saturation, but based on their chain length, they actually have some other healthier benefits. Then we have our butter, beef fat or tallow, pork fat, which is called your lard, and then chicken fat. Down the bottom, we have some of those different, what we consider to be oils, which are generally liquids at room temperature. Peanut oil, soybean, olive oil. Now we hear about olive oil all the time and how it's a very healthy oil to cook with. So if we look at olive oil, it has a small amount of saturated. It has a whole bunch of monounsaturated, and then a little bit of polyunsaturated. So each of these different oils, remember, all the side chains are going to be different, but overall, this is generally what we're going to see based on that composition. Usually, triglycerides rich in mono and polyunsaturated fatty acids are considered healthier, but it's a little more complex than just looking at the number of double bonds. So you've heard of saturated fats and you've heard of unsaturated fats, but what about trans fat or trans fatty acids? Sometimes you'll even see this on your nutritional label. Now there is a small amount, very small amount of naturally occurring fatty acids, or trans fats, sorry, I said that one wrong. Your trans fatty acids in beef, lamb, and dairy, a very, very small amount. But most of the time when we talk about trans fat, this is a byproduct that occurs during what's called catalytic hydrogenation. It's a fun word to say, catalytic hydrogenation. But more or less what this is that they have an oil, but the oils in their liquid state aren't necessarily the most shelf stable. They will go rancid. Did you know your oil can go rancid? So it's a big problem, especially like with olive oil. So that's why when you buy good quality olive oil, it's going to be in a dark colored and amber colored bottle. Glass is preferred over plastic because we want to protect it from oxygen and from the outside elements. But what will eventually happen is that it will break down, it'll be oxidized, and it'll go rancid. So to help get rid of that problem, to make it more shelf stable, what some companies will do is they will go in and they'll hydrogenate, or all of those double bonds that you have, they're going to break them and put hydrogen on them. Now, this is going to make it more shelf stable to where it'll last longer. But we have this issue that's going to occur. So one of the byproducts as this is happening is we start making what are called trans configurations instead of cis. Now earlier I made mention that whenever you have a double bond, I draw out my double bond. So here's 2 carbons, double bond, carbon. Now because there's a double bond in there, that means that that bond cannot freely rotate. The bond is just kind of stuck there. It can't move one way or another. So whatever is attached to these 2 carbons are always going to be on the same side. They're going to be on the top side or the bottom side. Now if they're both in the same direction, so they're both on the top or both on the bottom, that's called cis. Cis means that they're on the same, cis means same, and here for same we're meaning both top or both bottom. So naturally occurring oils have a lot of cis configurations. But a byproduct of this catalytic hydrogenation is that we start making some trans. So here's my cis, and I know it looks kind of weird. I'm holding up my fingers. You're like, what are you even talking about? So my 2 fingers, this is to represent the double bond. I have my thumbs, which are maybe a carbon coming off of the carbons, or maybe it's a hydrogen, whatever you want to think. And then my other fingers down here are the other side of the chain. That's cis. Now trans, you flip it around. One goes up and one goes down. Now this trans configuration, our body doesn't really recognize it. Yeah, there's a little bit that naturally occurs in our food, but a very, 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 very small amount. But when they started doing this catalytic hydrogenation, it introduced a lot more, and our body kind of threw a fit because it's like, I don't know what to do. It can't process it right. It doesn't know how to break it down. So trans fatty acids or trans fats are not good for the body. In 2006, the FDA actually required food manufacturers to list trans fats on their food labels, and New York City, along with many other places, has actually banned the use of these trans fats in their restaurants. And so a lot of times if you go to a fast food restaurant that fries a lot of foods, they'll say no trans fat, meaning that they have not used any of this catalytic hydrogenation to cause this trans configuration to occur. Because again, our body doesn't know what to do with it. So this is looking at that chemical structure if you have a cis or a trans configuration. So the top one is the cis, and this is what naturally occurs. We come across to that double bond. Our hydrocarbon chains are going to both go down in this case. They're both on the same side of that double bond. And so this causes where the chains can't line up really well with one another. It increases the volume, and so we have some unique situations that are going to occur. But if you have a trans fatty acid, here we have a double bond, but notice it wasn't quite as easy to tell. We don't have that great big kink. And so since we don't have that great big kink, our body sometimes gets confused on what's going on, and our body can't necessarily process this particular structure.